In this short video, we will use FIMMPROP's EME eigenmode expansion method to accurately and quickly calculate an MMI, a multimode interferometer. What we see here on the right side is a plan view of the structure created by 3 sections. And if I click on each of them in turn, the cross-section on the left side will update. And notice that this is around 1,000 microns long. The EME method worked by calculating the coupling between the modes of different sections. So what FIMWave will do when I click this button to show the scattering matrix, it'll calculate the modes in the 3 sections. And then it'll propagate the modes within the section. And then at the interface, these 2 interfaces between sections, it'll calculate the coupling between the modes. And this happens quite quickly in this case. So I'll click the button to start the calculation now. And the result is this scattering matrix that's displayed. What we're showing here is that if the input mode is the fundamental mode of the left side, this L represents left, then the modes exiting the right side have this power distribution. And we have 1 mode for each branch here. So we have approximately 23.5% of power in each mode. So not a highly efficient structure. And if we view the field, we can have a look at that for ourselves. So you can see here that the MMI is not correctly designed to maximize the transmission of power between the 2 branches there. So one thing we could do to quickly design this and improve this situation is to use the scanner. So I have a scanner already set up here, and I'm going to select to use the scanner on the device called MMI coupler, the one we've just been looking at. And I'm going to scan a variable called L. What is L? Well, it's a variable of preset, and it's the length here of this central section. So I'm going to scan it from, say, 300 to 500, and I'm going to do 128 steps. So when I click Scan Start, I'm asked to select what I want to calculate and plot on a graph. And yes, I want to calculate the power on the right-hand side in mode 1 and mode 2, in other words, the 2 branches. And when I click OK, we're going to do 128 calculations. And there we are, finished. So this really shows the value of using the EME method for this sort of design work. The first calculation took a few seconds, but then redoing the calculations at various scan steps is much, much faster because, if I go back to the device, the modes of each section have already been calculated. So all the software needs to do is reuse all of that data, and all it does is just change the length of this section. In other words, updating the scattering matrix associated with this single section. And that is a much faster recalculation. So we just did over 100 calculations of this device in a full 3D rigorous manner, which has a device which has a length of over 1 millimeter. And we have the answer of what a good length is for this device. So I can quickly get my crosshairs out, go up to the peak, and I would say at a length of around 413 microns, we get the maximum. So let's just see if that's the case. Right click, edit properties, and I'm just going to hard code it in, so to speak. I'm going to remove the variable and just set the number explicitly, 413. Calculate the scattering matrix. Yes, we've got much higher power transfer now. And if I click and plot the field, we've got a much more improved splitting into the 2 branches at the output there.